there are many things that we do, and recently the cyclone, there are cyclone shelters which have been specially designed, and across the coastal India, many cyclone shelters which have been designed by the CRC are still being used, and lakhs of people get shelter during the cyclones that happens, including the recent Fani. So this is the importance of this center. So I'll skip now. This I already talked. So basically, in wave propagation, this is a topic that I have taken interest of late, not very old. I mean, it's about 4 or 5 years, particularly because of my interest in structural health monitoring. And essentially, if you look at wave propagation, happens in solids for different applications. One of them is one of the things that we do in structures in that non-destructive testing. So that what you do is you push some ultrasonic waves into the structure, and the structure, if there is a defect, it interacts with that, and from that signature, either on the other hand or on this side, the reflected signal, if you analyze that, you should be able to see what is the quality of the structure, whether there are defect, and also and so forth. So where we need wave propagation, seismic wave propagation is known. Impact. So this is one of the things that we do in case of, for example, a structure has to be designed for blast loading. Okay, so what you do is a very high impact loading. So basically, it's a loading. Whole loading is applied in a very short duration, delta t. Okay, so and for that to understand the properties of the structure under that, for that, what you do is called split Hopkinson test, and there you actually have a wave propagation through impact, and then you see the behavior of the structure. So here again you need wave propagation. This is another example. For example, I was telling you, for example, you have a structure. This is a simple sort of cartoon. So this is a plate, and then you have for example, piezoelectric actuator, and you have a piezoelectric sensor. So when you actuate this piezoelectric actuator through some electric signal, then you can excite some ultrasonic wave, and then when you see on this front on the sensor, and then if there is a damage here, by looking at the sensor signal through a proper analysis, you should be able to tell where and what kind of damage is there. Now, so this is all simple, and then you have there can be thermal shock in case of nuclear reactors. Then there are if there is a piezoelectric material which is there in most of the electronic items, so you have thermal shock in piezoelectric media. So in n number of cases, you have a case where wave propagation happens, and then there are different types of waves. There can be body waves, there can be surface waves, there can be guided waves, and so on and so forth. So, and all depending on these, the nature of the waves becomes very, very different. For example, if it is a guided wave, it's very different from if it is a simple body wave, which is much easier to handle. So, and on the other hand, so this is the different kind of thing, and then on the other hand, you can classify the waves into narrow band as well as broadband. So narrow band wave will be something like, if you do a 50, so if this is the amplitude and this is the frequency, the whole amplitude remains within a small band of frequency. On the other hand, if it is an impact loading, so you have a wide band, so you have wide band of frequency in which the whole thing is acting. So therefore, the question which arises, and so these are the same thing I will not repeat. So now how do you actually analyze, because unless and until you can predict things, you cannot design. So this is one of the things that we have to do under structure, because you cannot design a structure or anything product through experiments. Okay, so that is not the domain that we can verify our analysis through few experiments, but we must be able to predict behavior of any structure or in any solids before we can design. Okay, that's the mandatory thing in structural engineering. Now, so the question is, how do we analyze all these things, wave propagation in solids generally? And so therefore, the effective tool which is there commonly used is the finite element analysis. But when you do finite element analysis for these kind of wave propagation problem, what happens is that, in fact, I was telling Professor Tarun Kant was asking me before this that where did you get the motivation? So I will now tell him the details. I told him very briefly that time. Essentially, when I visited Stanford in 2010, so they were working in these structural health monitoring problems, and wave propagation based structural health monitoring is a very very sort of the potential area for doing that. Now I used to see the students. I used to ask, what are you doing? They said that no, the program, I have now fired the program and the program is running, and that program is to run for 6 days, 7 days, 8 days. So what they are doing is basically they are solving a wave propagation problem. For 8 days they have to wait for that analysis to come, and then they will see that what is the result and whether it has crashed in between, maybe they have to restart it again and all that. So that is the problem, is that these are very high frequency waves. So high frequency wave means that the wavelength is very small, and if you have to model it correctly, then within that wavelength you have to have many elements, and then in the time also, if you have to correctly model the time domain solution, then you have to have very little incremental time, that delta t that is required for the analysis. So therefore it becomes a very large problem in case of computational, in case of conventional waves. So what you need is a very fine spatial and temporal discretization leading to large computation time. Not only that, that's about the computation time, but there are other issues. For example, if you use a conventional finite element, and if you have an impactor here and there's an incentive, it's a very simple problem, one-dimensional problem. So if you try to analyze this simple problem in conventional finite element, now this is what, if you put a velocity here, the velocity should propagate like this, and this is 0. Okay, but if you do a finite element analysis, this is what you are going to get. So essentially, instead of this, what you are going to get is this spurious oscillations. So that is called Gibbs phenomena, and that is very common. And whatever fine mesh you make, this cannot be removed from a finite element analysis. So these are the issues that are there. And thermal shock, I told you that nuclear reactor and particle accelerators and all this, and piezoelectric BGR thermal shock is important for this thing. So, and then when it comes to thermal, because some of you, for the briefing, when it comes to thermal shock, the conventional thermoelastic analysis, the classical one, some people say that's not good. Now, without going into merit or demerit of this, because I am not a specialist on that, but yes, the problem the classical coupled thermoelasticity which Biot gave has a problem calling that this is it gives infinite speed of heat conduction. Essentially, what happens is that as per that analysis, in no time the heat can reach from one end to another end, but it never happens. So therefore, to capture that into the physics, to capture that physics, finite speed of heat conduction, there has been different kinds of generalized thermoelasticity theories like Lord, Schulman, Green, Lindsley and all that theory. So what we have done is we have tried to use these theories for our analysis for the thermal shock problem, so that we can capture the second sound effect, and which gives very interesting phenomena, which is very difficult. And in fact, this gives rise to very sharp wave front, which is not there in classical thermoelasticity, and those sharp wave fronts is very difficult to again predict. And people have been doing it through analytical methods, but then analytical methods also have their own limitations, because you can do only for simplified geometry and all that. So if you have to do it for a normal general structure, you have to go for numerical methods. So these are the different aspects which are there into the whole system. And if I just have to talk about little bit of what are the methods which were available other than the conventional finite element. It is not that before me nobody has tried to look at these problems. Yes, there have been many people and there have been studies which are called semi-analytical studies, wave finite element studies, spectral finite element studies, spectral frequency domain analysis studies, But when we looked at this whole thing, what is turned out is that some of these methods have their problems in geometry. That is okay. I mean, for example, this method requires a uniform cross section of waveguide, which may not be there in real life problem. This method requires a periodicity of the structure, again may not be possible in real life problem. But this is a method which could have been, spectral finite element could have been a good method, and people have been claiming it for a long time that this is a very good method for wave propagation problem. But when we tried to test this method for a broadband excitation, and we found out that it is not giving very good result. So that means, see, all these methods that are there, and you do not know, no? User they will think that this is a wave propagation method, and so therefore you would like to use it for anything. You will not know that the result which is may not be actually reliable. So some cases they work and some cases it doesn't work. So these are the things that we have found out, and so therefore the motivation which came into our mind is that, is there anything that we can do, one particular method which will be applicable for different kinds of wave propagation problem in solids. So with that motivation, we have done from very basics and starting from one-dimensional and so on and so forth. So if you look at a one-dimensional wave equation, you will see that's a very simple equation. Everybody knows it's a first year, any graduation program, first year or even 12 it is taught. And what you see is that in the spatial domain you have actually this sinusoidal function which are the solution of this. So we took the clue from there, and so if you look at a one-dimensional finite element formulation for a simple bar, so this is what you have. You have this inertia, kinetic energy, this is the strain energy, and this is the virtual work which is being done by the external work. And so this is the Hamilton integral, that is a variational integral that you have, and these are the constitutive relations relating the stress and strain, strain and the displacement and so on and so forth. So there is something called partition of unity. It says that if a function fi pu is a partition of unity function, then the summation of all those should be 1, and if you multiply that with another function psi and do this summation, the function remains unchanged. That's the property of partition of unity. Now, so we try to take that into account, and this is the, for example, this is the displacement, and when you do a conventional finite element, what you have is that you have a unknown displacement here and a shape function here. So that is what is done in a conventional finite element. Okay, so what we said is that on that we want to make an enrichment function, and that enrichment function we would like to take from the physics of the problem, which is a sinusoidal solution. Okay, that's the basic. And this enrichment function, then if you apply the partition of unity, then you can actually multiply, because this is a partition of unity, actually sum of them is 1, so you can multiply this with this, and then this function will remain the same, and that is what we have done. So we have actually taken a bracket over the whole thing, and this is multiplied with this. So then what we ensured is that at the boundaries, the value of the approximation is same as the actual displacement at the nodes. So therefore this is what was changed, and we came up with, and we used the cosine and sine sinusoidal function to sort of take as this enrichment function, and came up with this solution for the approximation function for the finite element analysis, and put that into the Hamilton's principle. So this what we call as local harmonic basis function enriched finite element. And because we started with for the first time, we did not know which was good and which was bad, so we tried with another model. So this is one model and another slight variation of the model, which I don't want to go into details because that doesn't make a sense, because this was at the initial period we did. So we took another variation of that and then also tried. and then there is a global variation which also was tested with this. So without going into the details, I'll just come to the results so that we immediately understand what is the issue. So here, this is the problem. Again, it's a very simple problem. It's a bar, and you are giving a velocity here, and that velocity it should propagate at any point of time. So this is, so at 50 microsecond, the wavefront should have come here. This is the exact solution of this problem. Now, if you do this numerical solution, so this is what the conventional, if you look at this dot, possibly it is better here. So this is the one which is, as I said, the Gibbs phenomena takes place, and the finite element result gives this result. And if you take the global, we just try to check that if you take a global basis function, what happens. This is what the blue, again it's not so good, I mean it's slightly better, but still a lot of waviness is there. And then these are the two models that we saw, and we see that the green model is the best one, which actually virtually removes the oscillations, spurious oscillations. And you can see in all of them, what we have kept constant is the number of degree of freedom. So number of degree of freedom, if you keep constant and then change, this is what is the accuracy. So without increasing your computational effort, in this case we are actually enhancing the accuracy of the problem. Okay, so I think I have not even started. So okay, no, I'll do that. So what we have to see is that so the convergence, if you look at, we are getting extremely good convergence for the green one, and then if you take the narrowband solution that I was talking about, that if you take a tone burst solution, which is a narrowband excitation, which is used for actually structural health monitoring problem, and you see that if you took a conventional finite element, how away it is with this degree of freedom, and then if you take different kinds of thing, again the green color actually matches with the exact one, which you cannot actually indistinguishable, so you cannot see. So this is how, so both for narrow band and wide band, we have been able to show that how it works. And there is in terms of the computational efficiency, what we are showing here is that if you look at the, we can actually by 1/10 you can actually reduce the degree of freedom by 1/10 by increasing the sort of taking the higher order terms, but then it gives the similar kind of accuracy. So therefore, this is, and then there are different applications, and this is tried to show that it happens. And then this is the two-dimensional problem. So it a little bit more, more terms you can see. And again, for different kinds of problems, we have shown that this actually works very, very well. And then it is a piezoelectric material. Again, so you see the piezoelectric material, if you do this kind of impact, then what you get is an electric potential generated. And you see again that how the green color is actually, no, this is extremely hard to get a very sharp wavefront, and that is where the test of the method comes. Another interesting result I would like to show is that this is again in the, okay, so this is the convergence, how fast it converges, how fast it drops the error, you can see. This is the thing that is happening here. And another interesting result I would like to show is this, that even when it is not a wave propagation problem, it's a stress sort of singular problem where we do get a singularity and very sharp interface stress gets generated between a actuator and the structure. You can see a very sharp interface, and how that peak value, how this blue line, you can see it is here, but the actual stress will be somewhere here. So how the finite element, very fine finite element will not be able to do this problem, but we are able to solve this problem. So this has been now extended to thermoelasticity. I'll just 1 minute, I'll finish. So in case of thermoelasticity, again thermal shock when you give, so these kind of complicated stress wave behavior, and how very spurious oscillations are coming in finite element, but we are able to get a very clean sort of this thing out of this, and how the wave is propagating with different types of problems. So again, in case of if you do it,
please
yeah.
come to your last.
Yeah, so I'll come into the last slide. So essentially, what we have done is that we have actually, got this method, which is extremely good for wave propagation problems, not only for the mechanical, wave, but also thermoelastic wave, thermoelectroelastic wave, and we have been able to capture the both the narrow band end and the wide band, broadband end of excitation, and both for body wave as well as guided wave as well as surface wave. So all gamuts of wave propagation problem, we have shown that it is working. Thank you very much.